Hello everyone, thanks for attending our webinar today. I'm Paul Mania, Bioanalytics Application Specialist, along here with my colleague,
Nigel Herbert, Senior Bioanalytics Application Specialist. And today we are going to demonstrate the SoloVPE system for you. We're first going to go through a brief presentation, and then afterwards go through a live session of running some samples. As mentioned before, we will introduce the CTech SoloVPE system, its benefits, how it works versus traditional UV, and I'll also introduce some applications as well. At the end of the webinar, we will be doing a Q&A session as well. So again, this is just a brief agenda. We're going to briefly talk about vaccines and how the SoloVPE relates to them, challenges with UV spectroscopy, how slope spectroscopy works. We're going to be going through a high concentration and low concentration method, and then again, we'll be doing a live test on the SoloVPE system. So, as we all know, vaccines are a very important part of our everyday lives. We just wanted to go through some of the developmental processes of a vaccine and its typical roadmap. You'll first typically start with an R&D approach that'll take a few years just to identify the candidate. You'll go through some preclinical and clinical studies to test the safety and efficacy of the vaccine. Once it's proven effective, the FDA will go through a deep monitor and inspection of the vaccine, and afterwards it'll scale up through a manufacturing process, and then finally it'll be quality controlled. So today these are the common types of vaccines, starting with protein subunits, which are just fragments of the pathogen that can trigger an immune response. You can also use either a weakened or an inactivated whole virus, which can elicit immune response. You can also use a viral vector, such as AAV. And instead of hijacking the host cellular machinery, you can use it to mimic a natural viral infection. And lastly, you have your nucleic acids, such as plasmid DNA or mRNA, which can be used to provide your cells with instructions to trigger an immune response as well. Repligen offers innovative solutions for all key stages of the bioprocessing market. So we have solutions from upstream intensification methods such as ATF and TFDF through chromatography to filtration and fluid management. Our goal is to drive integrated smart systems that we can use for PAT automated use, and that is where our inline and at-line variable path length analytics products come in handy. Just going over some of the challenges with traditional UV. First and foremost, your assay time can be anywhere from 30 minutes to 3 hours. Additionally, it takes time for samples to be sent out for analysis, especially if you are transferring any samples. That can be very labor and time intensive. And lastly, doing any sort of manual dilutions or calculations, you're going to introduce dilution error, and that can be anywhere from 5 to 20%. So sample preparation for traditional UV generally has two approaches, which will be volumetric or gravimetric. Both will require a lot of time and skill, and you'll also need to ensure that your equipment is properly calibrated so that you are not introducing error from user to user. So how do we address all these challenges? What we do is variable path length spectroscopy. So instead of looking at a single absorbance measurement with a fixed path length, what we're going to do is actually vary the path length, which will allow us to unlock our concentration. So here you can see the Beer-Lambert law which states that your absorbance is equivalent to your molar extinction coefficient times your concentration times your path length. With our at-line and in-line uv-vis variable path length technology, what we can do is take multiple absorbance units at multiple path lengths to generate a slope. With that slope, we are able to measure a wide variety of concentrations at a much more repeatable and accurate way than traditional UV. So the SoloVPE system, which is a variable path length technology, utilizes the Carry 60 as its power and its light source. It does use a xenon flash lamp, so it is very powerful. It has a wide wavelength range of 190 to 1100 nanometers, and it has no warm-up time. So it is a very robust light source. So how slope spectroscopy works relative to both of our systems, what's going to happen is the fibrette will lower itself to the 0 path length position. Once it does that, it'll do a search algorithm to find one absorbance. Once it finds one absorbance, it's going to take a default of 10 data points going down. For our SoloVPE system, which is the at-line system, this data acquisition will be done about 1 minute. For our FlowVPX, which is our inline system, that will be done. It'll give you about 12 QC grade readings in about 1 minute. You can see on the right-hand side is your what your quick slope report looks like. The parameters that you want to look at the most is your path length range, which the SoloVPE has 5 micron to 15 millimeter path length range. The slope, which is the slope of the line, and the R squared, which confirms the validity of the result. So we want to ensure that you have at least 3 nines or higher as your R squared. And you can see for this example here, we were able to accurately measure about a 200 mg per mil MAB. So here I just want to point out 2 differences with slope spectroscopy. First, the light source is coming in from the top through the fibrette and out of the bottom to the sample vessel. So the fibrette is it's a solid piece of material. It's made of silica with a polyamide layer, and it is just emitting light straight through. So it is not a capillary. And the other major difference is, again, you're taking multiple measurements to calculate a slope regression. So you're not taking any absolute single absorbance measurements. The SoloVPE wants to know the change in absorbance over change in path length to measure a slope. Here's just an example of multiple modalities that the SoloVPE is able to measure. You can see whether it's protein, hemoglobin, gold particle, plasmid DNA, listerine. If it has a chromophore in the uv-vis range, the SoloVPE can accurately measure it, neat and undiluted. So the ASTM International Standard only updates this type of documentation every 5 years. So here they pointed out that there is potential risk with the traditional UV method having to perform dilutions to avoid saturation of the instrument. So this really gave our customers confidence that variable path length spectroscopy is a more beneficial method for them. As you can see here, both the at-line SoloVPE and in-line FlowVPX systems utilize variable path length spectroscopy, and the method is the same. The only difference is the acquisition reading and time, but in terms of the applications, both essentially cover almost everything. The FlowVPX, I would say, are more common applications revolve around continuous chromatography, dynamic binding capacity, and UFDF. Our technology has helped our customers succeed no matter the modality. Several companies have validated our technology for GMP use. We also have a variety of publications demonstrating our system's capabilities as well. Our instruments can be used in all functional groups and processes. Both will give QC grade measurements no matter the modality that is being tested, which allows for alignment on sample testing from group to group or location to location without any discrepancies. Here I just want to highlight a validation study that was performed by Regeneron a couple years ago. Here in a QC lab, they were able to save over a month's worth of time each year using our technology. The methods could also be easily transferred to other sites with minimal training efforts between each.
Thank you, Nigel. Thanks for covering how the instrument works and the applications involved. So I'm going to specifically be talking about high concentration and low concentration methods. So here on the screen, we can see that there's a high concentrated sample. On the left side, you can see the absorbance is going up above 2.0, and that gray area that we see, it seems like the graph dips down a bit. So this is what we call saturation. The absorbance is too high for the detector to discern any differences in absorbance. So anything in that gray region can be considered unreliable and actually underestimate your sample. So this is typical with UV spectroscopy, and this is a known concept, and that's why we're diluting our sample so we can get this value below any saturation limit. So we can see on the left side here that Beer's law tends to break down when it gets above 2.0 absorbance. And this does vary slightly from molecule to molecule. So proteins seem to saturate around 1.8, while DNA might have a higher saturation limit. But the goal here is to get linear data passing our 0.999 R² value or higher. So in this example, instead of using 10 data points, we use 7 data points. And you can see that on the right side, on the bottom of the graph, you can see the path lengths. So the path lengths only go up to 0.035 rather than going to up to 0.05, which is a 50 micron step. So the idea is here that rather than testing 10 data points, we're only going to test the 7 data points that are closest to the detector. This will keep the path length of light very small so that the absorbance stays below any saturation limit so that we don't have to underestimate our sample. And so as you can see here, that gray region that we would have measured would be cut off when we go to our 7 data point method. And on the right side where we see the red lettering for the path lengths and the absorbance, those are saturated values that if we exclude them, the line becomes more linear and the concentration would meet more of an accurate of an estimation and we wouldn't be underestimating. So as we go above that saturation limit, the absorbance values don't change as much, so we'll need to eliminate those values. And so we can see here that using the default settings for this 220 mg per mil monoclonal antibody, we were underestimating the sample when we were measuring with 10 data points. And we also had some difficulty getting consistent results. As you see, the relative standard deviation reached 4%. So that's all involved with measuring saturated values, which aren't going to be consistent. If we use that high concentration method where we lower the data points, we're able to stay below saturation and not read those saturated values, which brought our concentration back up to 220, and it kept our relative standard deviation. Our consistency was very good with this reading. So suggested changes to the method, I just mentioned that we're going to lower the data points from 10 to 6 or 7. We didn't choose 5 data points, so 5 would be the minimum that the SoloVPE requires. We wanted to give the software some flexibility, so in case a data point comes out of linearity, the software will automatically cut the data point off to leave 5 consecutive pieces. So at the top here, we have mixing. Mixing is extremely critical for all SoloVPE measurements. Because we're measuring at different path lengths in the solution, it's important that the sample is the same throughout. So especially with high concentrated samples, those tend to settle a lot faster, so mixing just prior to measurement is going to be very important. Plastic vessels are highly recommended, especially with high concentrations, because you can eliminate any risk of carryover. It's very difficult to clean high concentrated sample. And you would actually need to use a glass vessel if you wanted to clean those. So plastic or use and throw. So all of these settings that I'm discussing, you would modify them in the quick slope menu, and then you would save that method so that you wouldn't have to configure any of this anymore, and you can actually load this and run it for any of your samples. Lastly, I didn't mention this before, the carry 60 averaging time. So the carry 60 is the spectrophotometer that we're attached to, and we're just going to increase the time that that lamp is going to spend on each data point. This helps eliminate outlier data, so we would just increase it from 0.5 seconds to 1. That's all done within the quick slope settings as well. Now that we're done with high concentrations, we'll go on to low concentration. This is an example of a wavelength scan of a very low concentrated antibody. And the idea here is to see that there really isn't anything to observe. It just seems like a flat line, and that's because the concentration is so low that we can't really use a spectral scan to accurately measure this. With the SoloVPE, we can measure at 10 different path lengths. So typically, if you wanted to get this type of result on a traditional UV, you would have to do 10 different dilutions and measure them individually. For the SoloVPE, each of those lines represents a different path length. So the top line would be the furthest path length away from the detector, while the bottom one would be the closest. So essentially, you can get all of this information within a minute on the SoloVPE by using a scan. So some of the challenges that come with measuring a very low concentrated sample is that the absorbances aren't going to change very much from reading to reading. So you can see on the right side there, we're no longer bound to the 5 millimeter path length or even 0.05 millimeters that we were using for our last sample. We can now go up to 15 millimeters to obtain our result. Now, we're using longer path lengths so that we can have more light get absorbed on its way to the detector. Because we're using such low absorbances, we want that absorbance to actually change more considerably from one reading to the other. So that last method, we were using 10 data points. We're actually going to use a very similar concept to the high concentration method here, and we're going to lower the data points to 7. And the reason why we're going to do this is because taking 10 steps from 15 millimeters to 0, it's going to take larger steps if we use 7 data points rather than 10. So if we take a larger step, we're going to change the absorbance more, and all of this is going to help with our linearity. So the main idea that is important to understand here with low concentration, if you're using a regular method with a plastic vessel, you're going to be very limited with your path length range, and the method is going to be very inconsistent if it falls below a certain slope value. So you can see on the left, these slopes are 0.02. If you want to equate that to UV, that would be 0.2. So these are extremely low slopes, and without the low concentration method, we see the consistency falls off at 21.68% relative standard deviation. Using the low concentrated method, lowering the data points, and increasing the averaging time, we brought the results down to 1.45% RSD, and we can see that they're extremely consistent here. So suggested changes for the low concentration method would be we need more path length range. We need more than 5 millimeters. So the other option we have is the large glass vessel. So that's going to be 2.5 milliliters of volume. And it's very common for any of our customers to do any buffer evaluations with this large vessel. So right below that, we have baseline correction, and this is directly involved with the buffer. So any low concentrated sample that has a buffer, there should be an evaluation to see if that buffer actually contributes to the result of your sample. So basically, you measure that buffer 3 times, see if you can get a consistent result, good linearity. And if you do, you would see if that contributes to at least 1% of your sample concentration. So there's buffer evaluation step that can be used, and if you have a low concentrated sample, it might be very critical to get accurate results. And lastly, carry averaging time. This is actually very important for low concentration. Because we're working with such low absorbance values, we tend to find more outlier data appearing because the instrument noise is actually coming into play here. So if we increase this averaging time, we can lower the amount of outlier and make our results much more consistent and hopefully more linear than using a different method. Okay, so now that we're done with the presentation, we're going to go into live sample testing right here on our SoloVPE. We're going to measure a high concentrated plasmid and a low concentrated protein. So Nigel's going to talk a little bit about the system and go into the software.
Thanks, Paul. Just for all the viewers, this is, again, our SoloVPE system. We have our Agilent Carrier 60, which is our power and light source on the bottom. The SoloVPE instrument, which is going to be taking all your measurements here. The connection between the Carrier 60 and the SoloVPE is this delivery fiber, which is made of the same components as our fibrette. So it is made of silica quartz. You're going to insert a sample on top of this detector window here, close the cover. This will move down, and then it will do variable path length to generate a slope. You'll insert your attention coefficient, and then a concentration will come out. What I want to do first, before going into sample preparations and running a sample, is demonstrate some components of our software and how we comply with 21 CFR Part 11. So, with the Viper software, this is the platform that we're going to be using to take all of our measurements on the SoloVPE. Before I get into the method, what I just want to briefly discuss is the secure VPT settings. Here is a compliant package that you can purchase with your SoloVPE in order to have your system in a GMP environment. What you can do here is in the user types tab, you can create users and groups. And with those users and groups, you can define roles within the software, as well as roles within different applications. So you can make them have an admin or super user role, or just make them a user or reviewer level. Going into user management, this is where you would actually create your users. Feature access is where you can limit the specific permissions within each application. If you go into eSign app configuration, this is where you can set the specific eSign events that will occur. So for the start of data collect or end of data collect or saving a method, you can authorize an author, a reviewer, or an approver to perform an e-signature. We also have the eSign user configuration. This is where you can select the user and define what type of e-signatures they can apply. And lastly, in the method library, this is where you can deactivate old methods. Okay, so after going into the secure VPT settings, what I'm going to do is go into QuickSlope, which is the software application that you'll be using to take all of your concentration measurements. What you want to do to make a high concentration method is change all the parameters on the left-hand side. First, you want to ensure that your slope mode is defaulted to quick, so it's going to do the quick slope algorithm. You want to use the plastic vessels, which are chosen here. You want to hit this ellipses next to wavelength and change this to 1. So we're doing a 1 second averaging time. You want to change the wavelength to 260 because that's where plasmids absorb. You want to apply a known extinction coefficient. So for a plasmid, it is 20 mils per mg centimeter. The rest of these parameters can be left off. We're not going to apply scatter correction. We're not going to do reps, and we're not going to run a baseline. But what we can do is hit this ellipses next to path length to limit the data points to 6. And then once that's all done, what you want to do is insert your sample name here. And then we are ready to run the method.
Thanks for setting up the software, Nigel. It's very important to set up the software parameters first, just so we have the software ready. So as soon as our sample's ready, we can just put it into the holder and click play. We don't want to give any time for that sample to settle or evaporate. So first thing I'm going to do to run this sample is insert my fibrette. Typically, your fibrettes come in these containers like this, but each of the system will come with fibrette dispensers so that you can take fibrette one at a time from the side, and then basically you just insert like this. You push up till the fibrette slides along your hands, and then you're going to actually push up on the silver piece, and that pulls the fibrette down a pinch. I'll explain a little bit about why we're doing that action when we're running the sample. So for this, we're going to need 120 microliters maximum for 5 millimeter path length limit plastic vessel. So the minimum volume you can use in here is 20 microliters just to cover the bottom. We're going to use 100 right now. So this is our plasmid, and we're going to vortex it first, so it's very important to mix. I like to do a little inversion just to make sure there's nothing in the cap.
I also wanted to note that it's very imperative for you to wear gloves when you're inserting fibrettes or doing anything with the SoloVPE system, since it is light-based, so any oils from your hands can really contaminate the measurements. So wearing gloves is a good technique to implement.
So I'm going to pipette 100 microliters into this plastic vessel. Now, something I'm always being careful for on the SoloVPE is making sure that there's no bubbles. So any bubbles on the bottom, very large bubbles, any bubbles on the bottom would interfere with the result because it would be going through air and liquid medium. So once you verify that there's no bubbles, you can go ahead and put your vessel into the holder. We already put our fibrette in and pushed up on the silver piece. You can do that again if you think you forgot. So we're all set here. And now we can just click play on our method.
So I'm just going to hit the play button to run the method. Anytime you hit the green play button, this prepare sample dialog box will pop up to just make sure that you've done the correct steps, which Paul did previously. We're going to press OK. And then the SoloVPE is going to go down to its 0 path length position. It's going to do its internal search algorithm to find one absorbance, and then it's going to take 6 data points going down with the method parameters that we set on the left. This acquisition is going to take about a minute, and then afterwards we'll go through the report and show all of the data that's associated with the quick slope run.
And I guess I'll take some time right now to explain why I pushed up on that silver piece after I put the fibrette in. So the Solo doesn't actually have a sensor in here, so we need to make sure that the fiber optic glass rod, the fibrette, touches the bottom without having a sensor. So when we push up on that silver piece, we're actually pulling the fibrette down, so when it touches the bottom, the fiber optic line stays loose and it won't get crushed.
Perfect. So after a run is done, we get this send home prompt. You can either press close to run a sample again, just because the fibrettes are one and done, or you can hit send home and discard of the fibrette. So in this case, I'm going to hit send home, and then you can hear and see that the SoloVPE is going to go to its home position. And then we're just going to quickly look at the data. You can see first is your graphing section here. So we have 6 data points. It's well under 2 absorbance, and it essentially went from 5 microns all the way up to 0.03 millimeters. So you also have a quick view on the right-hand side, which just shows the most important results, being your concentration, your wavelength, the R squared, and your slope. Under the reporter section, you have all of the information related to the method, the run details, your last quick check and coupler check, which are maintenance procedures, as well as the audit log. If you go to the slope data here, you have a little more detailed information on the slope that was generated, the R squared, which is well above 0.999, wavelength concentration, the exchange coefficient, and a timestamp. For more detailed information on the analysis of the run, you have the raw data, which will show the absorbance measurement at each path length. So now that we're done running the plasmid, we will move on to the low concentrated protein, which will just be BSA. So what we want to do first is Paul will discard of the all the materials that he just used to run the plasmid.
So one good tip here is anyone that in the future gets a SoloVPE, when you take the fibrette out, just make sure you leave the sample in there so that in case the fibrette goes back to the bottom, it actually just went inside the sample container and you won't touch the glass below. So we'll remove this.
Now we're going to set up the method for the low concentration sample. Similarly, we're going to be working on the left-hand side of the quickslope application. So we want to ensure that quickslope mode is enabled. You want to change your sample vessel to large. You want to bump up your averaging time to 1 second. And then you want to keep your wavelength at 280 since we're measuring a protein. We can enable the extinction coefficient, and the extinction coefficient of BSA is 0.667 mils per mix centimeter. We're going to keep scatter correction and rep mode off, and then we can limit our data points here to 7. If you were to enable baseline correction, you would press on here, and then you can see that this is now denoted with B to run baseline. You would just need to insert your sample name, and then this would turn green, and then you would run the baseline. But we did evaluate this buffer previously, and for this run, it is best that it's off. You will get actually more accurate data. So what I'm going to do is just insert the sample name here, and then I'm going to pass it off to my colleague Paul to prepare the BSA sample.
Thanks, Nigel. All right, I'm going to prep the BSA. We're going to use a large vessel since we're using a low concentration. I got my BSA here. Just give it a quick vortex and a couple inversions. Always want to make sure everything's mixed properly.
Definitely.
So I'm going to go for 3 aliquots of 800. And the idea is to have around 2.5 milliliters. Anywhere from 2.2 to 2.5 should be okay. All we're really trying to do is make sure that the liquid height inside the vessel is going to be 15 millimeters in height so that our fibrette can use all 15 millimeters of that liquid height to evaluate the absorbance. So we're going to put our sample in the holder. We're going to get a fibrette. And we're going to insert it here and push up on our silver quickset coupler, lower the stage, and we should be all set.
Perfect. Thanks, Paul. And then going back to the Viper software, what we can do is press the green play button to run the method, and then again press OK. So similarly, what the SoloVPE is going to do, it's going to go down to its 0 path length position, do its search algorithm to try to find 1 absorbance, and then this time takes 7 data points going down. We'll see in the data too that because this sample is so dilute, odds are that we actually won't find 1 absorbance. It'll probably be a lot less. But as Paul mentioned previously in the presentation, using that longer path length step will give us our best accurate and linear chance for the result.
And I was mentioning before, or Nigel was mentioning about the buffer. So you can do a buffer correction or a buffer requirement test. Essentially, what you're going to do is test your buffer and quickslope at the wavelength that you're desired. Test that in 3 repeats, and then record what your % RSD and your R squared are. The idea is that you want to make sure if you do implement buffer correction that the buffer can be measured consistently.
Okay, so now that the run is completed, we can now tell it to go home. Again, you have your quick view parameters on the right. So all the results, saturation, your wavelength, R squared, and slope. And then all of your data is in this reporter here. We have our slope data, and then again, you have the raw data. So you can see here the absorbances that were captured at each path length. And then you can see that it wasn't able to target one absorbance just because of how dilute the sample was. But its ability to go to longer path lengths gives us the best chance of success. And you can see we were able to measure about a 0.1 mg per mil.
And as you can observe, the slope that we recorded was 0.0085. So if you wanted to measure this on a traditional UV, it would be 0.085. So the SoloVPE has a very large dynamic range where it can measure very high and very low slope values. Something else that is interesting to note in here, you can also report this information into a PDF very easily via the report wizard. So you have all of your categories on the left side, which you can reconfigure. You can actually slide one of these above the other one to show if you want to reorder them. And you can save all these configurations to a specific saved report method so that everybody's reporting in the same way. And the Viper software uses a SQL Server database, which is electronic data storage. So if you ever want to obtain any of your data in here, all you're going to have to do is click on Open Data, and it should be stored within the computer's database.
Awesome. Well, thanks so much for tuning in, and thank you, Paul, for your help for the demonstration.
Thank you, too, as well.
Yep. And now we're going to go to our Q&A session. So if anyone has any questions, please feel free to ask.